Yeah, hello everyone. Today we will discuss about boost converter. So in the last class we discussed about the buck converter in the case of isolated DC-DC converter purpose, and today we will discuss about the boost converter. So as you know, what is the purpose of boost converter? A boost converter is also a step up converter. Okay, a boost converter is also a step up converter. Step up converter. That means the output voltage is greater than input voltage. The output voltage is greater than input voltage. So here how it is possible in this case, an intervening inductance stores the energy per time. So when it is stored the energy, okay, inductor has its capability, right? When it is want to deliver, so that at that condition, when it want to operate in a boost converter case, the input voltage is added with the inductor voltage so that both are going to give the output voltage. So that's why the output voltage is greater than input voltage, or the input voltage is less than the output voltage. So here, what I mean to say that, so in the one case, we are going to store the energy in the inductor, and when you want the converter to be operated in the boost converter mode, that energy is going to release, and that energy is adding with the input voltage. So input voltage this one and inductor voltage is this one. So both are together added will be giving the output voltage. So in that case, the output voltage is greater than the input voltage. Okay, so we will discuss some applications of this where it is useful here. The applications of boost converters where we use generally. Okay, so let me take first here. Here, I have a battery. So this is an EV battery. I wanted to charge, or with this battery, I wanted to run motor. So we have a voltage source inverter is there. So this is driving the motor. So this is a motor, and this motor which drives the wheels, right? So this is generally in the electrical. Okay. So here the availability is here that I have a battery. So this battery has to drive this motor. So as you know, this is that you cannot do it, right? So here the input voltage is assume a less voltage. So this small or less voltage is not able to drive this motor. Okay. So we must do some voltage step up. Okay. So in that case, so we have to use a one converter called as boost converter. So this boost converter, so what it's doing is it is stepping up the voltage or increasing the voltage levels so that it is going to give the voltage to voltage source inverter so that it is going to convert into the AC, and thereby it is going to drive the motor, thereby it is driving the wheels. Okay. So here the voltage which you are getting here is VDC. Okay. And here it is a here the voltage is VM line. Okay. Motor line voltage. So this is the first example. So wherever the battery voltage is less, which is not able to drive the motor, so in that case, we have to use a converter called as boost converter. This boost converter is boosting the voltage to the required level to run the motor. Okay. So here, the input voltage which is available at this VSI voltage source This VSI is voltage source inverter. Voltage source inverter. The input voltage available at input of VSI is how much, you know that. So we know that, we assume this is a line, VM line, right? VM line, right? So the input voltage before this one is VM line divided by 0.6, that will give the VDC. Okay. So what are the VM line voltage is there here? So before this VSI converter, it has to divide it by 0.6. Okay. So that is the first application of this boost converter. And come to the second application, application 2. Do you know, we have been discussing about the one specific important application is of the electric vehicle is regenerative braking. Regenerative braking. What is meant by regenerative braking? So regenerative braking, so specifically you can take it as a motors with DC motors, with DC motor drive. Regenerative braking with DC motor drive. So one example, one practical example in India, that in Delhi, so the metro, Delhi metro have saved so approximately 4 crore rupees, and that is not now, 10 years before. Okay, so they have saved, so with this regenerative braking, approximately at 4 crores. So the application for this one is to carry the luggage in the airports or else in the metros. Okay, so in the metros and all, so to carry the luggage purpose mainly. So they have saved metro, Delhi metro. What is the amount they've saved is 4 crore rupees. That is 10 years back. Okay, so what is this regenerative braking is? So regenerative braking, it converts kinetic energy stored in the wheels into electrical energy. Okay, so here, so in the before example, so when you are giving the voltage to the boost converter here, it is stepping up the voltages, thereby you are giving the voltage to VSI, it is converting into the AC, so that the motor is driving the wheels. So when the wheels are running, okay, when the wheels are running, it stored the kinetic energy in the wheels. Okay, so that kinetic energy can be converted into electrical energy by feeding back to the power, and that energy is again feeding back to the power supply, so that it will store the energy, and when the energy saved or stored, so that the range of electrical vehicle also can be increased. Here the one advantage is, the issue with the electric vehicle is the range. With the one charging of battery, how much distance it is able to travel, that is the issue here. Okay, that is a major thing, or major research is going on that. Okay, when you run the motor in the regenerative braking case, so that it will store, recharge, or it will give you back the energy to the battery, so that energy is saved. When the energy is saved, the range of electric vehicle also can be improved. Okay, so that is a major advantage here. What is the regenerative braking here? So it converts the kinetic energy stored in wheels, converted into electrical energy, and once it is converted to electrical energy, and it is again feeding back to power supply. So what happens from this? So energy is saved. So that is the first example. So you know that when the energy is saved, when the energy is saved, so that which will increase the range of electric vehicle also increased. Okay, so that is the second example. Now if you come to the third example, so in IC engines, okay, internal combustion engines, okay, so you know that we have a batteries in the IC engine. Let me assume that is a 12 volts battery. 12 volts battery. Okay. So with this 12 volts battery, I have to feed some the applications here. Okay. So I have a different application like EC electronic control units are there in this vehicles, and AC is air conditioners are there, and infotainments are there. Infotainments means information and entertainment. Infotainments and some ACs and lighting. Okay. So wherever for this all the application, this 12 volts directly is not sufficient to drive it or feed it, right? So there we have to increase the level of voltage which is suitable to these applications, and there we are going to use boost converters. Boost converters. Okay. So to feed all these appliances with this 12 volts batteries, we need DC converter. So here we required DC converter, DC to DC boost converter, when load requires more than 12 volts, Is it right? So we have a 12 volts only, but this load requires more than 12 volts. So what we have to do? We have to increase the load voltage. Okay. So by using a boost converter, when you increase the voltage level, it is more than 12. When increase of more than 12, then we could be able to feed them to the all these applications in the IC engine, so that this all can be. So these are the features that we have in the IC engines. Okay. Nowadays, all the there are many features are there in the IC engines. So those are the major features with this DC boost converter. Okay. Now we are entering into the boost converter topic here. So up to now we discussed about where we are going to use this boost converter. Now come to the actual operation and circuit of the boost converter. Okay. So assume here I have input voltage source, V input, and here I have an inductor, intervening inductance here, and then I have a switch. Yes, this is a switch. It may be a IGBT or a MOSFET. This is switch S, and then followed by a diode here. This is a freewheeling diode, and we have a capacitance, and then followed by a resistance, a load resistance. Now, voltage across this load resistance, we can assume it is a V output, and this is a capacitance C, and it is to limit or filter to limit the ripples in output voltage. So this is inductance here. So it stored the energy storage element. I told you, right, how in the boost converter, the inductor plays a vital role because it stored the energy. This energy is added with the input voltage. Input voltage plus inductor voltage as inductor can be added together and can be feed the load. So in the boost converter. So this is the boost converter operation here. This is input voltage, inductance, and a switch and a diode. D for the freewheeling. Now, when you look at this here, when the switch on or off, so that for example, just forget about this switch here. So when you give an input voltage here, directly the load voltage is going to get, okay, load voltage current is coming here. Okay. Now when you are, this is in the absence of the switch. Now we will see the uh, switch operations. When the switch on, when switch on, when switch on, what happens here? Then switch will be on here. So I'll draw the circuit. So this is the circuit, supply voltage Vin, inductance, and a switch on. So when it switch on means it is acting like a short circuit here. Okay, now this is a short circuit will be when the switch is on. Now here, whatever the input voltage is there, that will be there across the inductance. So this is V input. Now, because of this inductive polarities, because of this inductance polarity, when the input voltage is applying across this the inductance, so because of this polarity, this negative will be here, it is anode here. So negative is connected to the anode, so that because of this polarities of the inductance, the diode will be in the reverse bias. Because of the inductor polarities, the diode will be in reverse bias. When the diode in the reverse bias, so it will be an open circuit here. So rest of the circuit is not connected with this source. Okay, rest of the circuit is not connected. So I'll be showing that also here. So this is a V in, and when the switch is on, it is acting like a short circuit here. The input voltage will be there across this one inductance. And now when because of the polarities of the inductor, the diode is acting in a reverse bias. So this will be capacitance C, and this will be a resistance R. Right, clear? Now, before this, whatever the capacitance is charging here, so that is going to charge through the resistance. Okay, capacitance is going to charge into resistance. Capacitance is going to charge into resistance. Now, come to this discussion here. What is the voltage across inductance here? What is the voltage across inductance? Voltage across inductance VL. So what is the VL here? This VL is equal to input voltage, right? It's a closed loop. What are the input voltages there? That will be there across inductance. That is equal to V in. Okay. Now, if I write this equation, L into voltage across inductor formula, L into delta IL divided by, so when it is on, when it is this voltage here during the on time T on. Okay. Now, can I write this here? VL is equal to L into delta IL into dt. What is my dt here? Duty cycle is equal to on time to the total time. Okay. Now, on time is T on is equal to D into T. Thus, D into T I have written here. So, VL is equal to L into delta IL divided by dt. From this, VL into VL into dt is equal to L into delta IL. Okay. Now from this, I can write it as a V in into dt is equal to L into delta IL. The same equation here, right? So this is taken as one equation. Now we'll discuss the when the switch is off here. Up to now, this is a discussion when the switch on. Okay. Now when you want to turn off the switch, what is the condition here? Okay. When the switch off. Okay. Now look at this circuit here. So in this circuit, when you turn off the switch, so this is it will be off. So we will see how the circuit is look like. So we have an input and inductance. Okay. Now here, so when the switch is off here, now the voltage across input and also voltage across inductor can blast their both the voltage across the diode, so that diode will be in the forward bias and this will be circuit. Okay, this is circuit. Now when it is connected like this, the input voltage V in and input voltage across inductor, both are blasting across the diodes. Thereby, the diode will be in the forward bias. So when the diode is forward bias, we can also take it as a short circuit like this, a capacitance and a resistance. Right. Now V in, VL. Now it is a capacitor C and voltage across this. I'll be writing here V output, and this is also same. Okay. Now here, so when V in, okay, so when the switch is off here, so you know that inductor is not going to change its current direction immediately, so it will change its polarities. Okay. Now with this, so this output, if I apply KVL in this loop, if I apply KVL in this, so what will I get here? V input plus VL is equal to V output. Yes, right? From this, VL is equal to V in minus V output minus V in. Okay. This is the voltage across inductor during the switch off condition. Okay. Now here, L from this VL is equal to L into delta IL divided by, so in the on time we have taken a dt, right? So remaining is 1 minus d into t. During the off time it is 1 minus d into t, in on time it is d into t. Okay, right. Now from this VL into 1 minus d into t is equal to L into delta IL. So take it as equation number 2. Okay. Now one observation here also. So during the switch off, when S off here, so inductor releases energy. So when the inductor releases energy, so what is the current situation there? So current is going to fall. Okay. So current comes down. Current comes down. That is one observation to be made. Now, if I equate equation 1 and 2 here, this is delta IL and this L into delta IL, and it is also L into delta IL. If I equate those two, so that I'll be getting V in into dt is equal to V output minus V in into 1 minus d into t. So from this V output is equal to, if I write V output is equal to, so this V in into 1 minus delta t coming in this side. So this will be, so that V in delta t get cancelled. So you will be having only, so I'll be writing one more step here. One V in output into 1 minus d into t is equal to V in. so that V output is equal to V in divided by 1 minus D into T. So this is the output voltage expression for a boost converter. So this is for boost converter. If you remember the previous one, what we discussed for a buck converter. So buck converter output voltage expression, output voltage equal D into V input. So this is for buck converter and this is the equation for boost converter. So boost converter output voltage is equal to V input divided by 1 minus D into T. So if I write here, so V output divided by V input, what is the expression we can write here? 1 by 1 minus D into T, right? So it may be useful in the case of problem solving. So this is the output voltage expression that we have here. Now we'll have to draw the waveforms for this, right? Now one small observation here. Okay, so when the switch is on, right? So here, if you keep the switch on for a long time, like this, you make it for a longer time, T is longer time, so that at the time when the T is more, it is the inductor also stored the energy for a longer time. Energy also stored for a longer time, so that the boosting voltage also will be the output voltage of the boost converter will be long values, big values. Okay, like if you want to boost the value to a high, then you have to switch on for a long time so that inductor energy can store for a large amount of energy in that long time, so that it will boost the output voltage. So similarly, if you decrease the time is smaller time, okay. If the switch on for a less time, so that inductor store the energy for a very less. Okay, inductor store the energies for a less, and then boosting property also will take a small amount of boosting voltage also can possible. Okay, so here the observation to be made here that, okay, so point to be noted our observation here. So if switch closed for longer time, so what happens? More and more energy will be stored in inductor, so that the voltage can be boosted up to large values. Okay, so like the counter opposite for this, if the switch on for small less time, so that what happens? Inductor energy stored is also less, and boosting value also, energy boosting also less. Okay, so that is the observation to be made here. Now we have to draw the waveforms here. Okay, so now apply the pulses here. So this is the time, and here the pulses I am applying for this: on time, and it is off time, again on time, off time. Okay, so now when you turn on this, so these are the pulses for the switch. Okay, now when you turn on, so what happens? Current during the on time, the inductor will charge, right? So inductor current will increase. Inductor current will increase from a point here and up to this maximum, and then it is coming back to the point here where it started. Okay, to and then again, it is increasing up to the maximum, then again, it is circulating. So this is IL current, okay, inductor current. Now, if I take this as like this will be on time, and this is an off time, and total is, as you know, this is total time period. Okay. Now, if I want to draw the voltage across the inductor, so this equation is current through inductor. This is a pulses, right? Now, if I draw the extend this limits. Now, during the on time, what is the voltage across inductor value? VL is equal to VN, right? During the on time, the voltage across inductor value is equal to Vn. So this is will be totally, I'm drawing the VL equation, and this limit is Vn. So after this, okay. Now during the off time, what is the voltage across inductor? It is in on time, right? When the switch is on. During off time, what is the voltage across inductor? Just now we have seen here. During the off time, what is the voltage across inductor? This is right. So it will be V output minus. So after you boosted the voltage, from that you have to subtract the input voltage, then you will get voltage across inductor during the off time. So I will be drawing this red pen. So this is voltage. This voltage is V in, V output minus V in. Okay. So this is the area which is called as A1, and the area which we call this as A2, where A1 is voltage across area of the voltage across inductor, and where A2 is voltage across inductor, but during the off time, A1 is during the on time. Okay. Right here, point here to be noted. Whatever is the energy taken by the inductor on interval and is giving back to the inductor during the off time. Like I want to say that. So in this A1 energy, in the A1 period, the inductor is taking the energy. Okay. So that the same energy is going to deliver during the off time to the inductor. So inductor charging and discharging can take place, right? So whatever is the energy taken by the inductor in on interval and giving back to giving back by inductor during off interval. So when it is giving in on time and it is giving back to in the off time. Okay. So by the law of conservation of energy, what you can by law of conservation of energy. So the energy in the on time is A1 must be equal to A2. Okay. The energy in the on time must be equal to energy in the off time. Okay. Now this is the discussion regarding the boost converter here. So right, I wanted to note some equations here. What is a change in delta current during on time? During on time, during on time, what is the change in delta IL current? Okay. So as you know, delta IL is equal to VL into delta T divided by L, right? So this will be V in. During the on time, VL is equal to V in, and this delta T is, this will be in dt divided by L. So this is the equation during the on time. On time. Okay. So change in delta current, inductor current. Change in inductor current, that is delta IL. So if we discuss about during off time, so delta IL during off time, so delta IL is equal to VL into, so it is a dt means it will be a 1 minus d into t, right? So divided by L. Okay. So delta IL is equal to, so as you know, voltage across inductor formula, V output minus V in into 1 minus d times of t divided by L. So this is the change in inductor current during off time. During off time. Now, what is the voltage across change in voltage across inductor here? Delta V. These are just formulas for the case of problems during off time. So this delta V, V is equal to Q by C, right? So delta V means delta Q by C. That is equal to IL into 1 minus D times of T divided by capacitance C. Now, if I want to draw the right further here in this, so here I just want to draw here a case here. This is a voltage, and the pulses which you have applied is this pulse on time. This is off time, and if I talk about the inductor current here, okay. So this is the inductor current, and this is the inductor current during on and off times. Right. Now, if I take delta IL peak to peak here, this is the average of the IL will give a change of currents here, delta IL. This is the delta average of the current, delta IL peak to peak. So I wanted to find the current here by using this here. So we have IL is there, right? So this here is a triangle is formed, right? So what is the length here? It is if I take this is length is delta IL by 2. Okay, and this is the time is the total T of it. This will be in the half time. This will be in the half time. So it will be a Ts by 2. So right, if I take the delta V is equal to delta Q by C, that is equal to half into what is the energy stored is half CV squared. So this will be a triangle half into the height into the base, right? The base is Ts by 2 and height is delta IL by 2 into Ts by T divided by the switching frequency or TA by 2. You can also write anything. T by 2 into half C, right? This is 1 by C. So this will be delta V is equal to delta IL into T divided by 8 into C. This is the formula. Okay. So here the height will be half of this IL. That's delta IL. That's a delta into IL. And this will be on time, it is half of TS. This will off time, it is half of TS by 2. So half of this will be TS by 2 half. And TS means T or TS both are same. Switching frequency of this one converter. Okay. And this is the regarding of అసలు మంచిగా పడుకున్నాడు. నేను తిన్నానే.